Should be on DegreeWorks. If you just log into DegreeWorks, it should list it there at the top. Okay. I hope everybody had a relaxing spring break, productive spring break. I know the canoe team was hard at work over break. My goal was to have exam one, it should be exam two. My goal was to have the exam graded by the time you all got back, but I was actually pretty busy in the background over break with just some administrative stuff, so I didn't have a chance to finish it. So my goal is to get that done this week. I don't have this here on the announcement slide, but I'll just go ahead and announce that on Friday I'm canceling class in lieu of a pre-recorded lecture. Okay, so I'll have a pre-recorded lecture on YouTube on Friday and a homework that's due Monday. And I think probably most of you could guess why, but if not, we have our Regional Virginia's Conference, the canoe race and the Steel Bridge is this week. So I'm going to head down to Beckley on Friday and cheer on the team and whatnot. So yes, I'm canceling class on Friday. I know it's been a while since we've looked at this, but I guess I'll just get back into the mode. If y'all remember, the last homework that we had was the AISC column curve homework, the Excel-based assignment. How did that go? Was that pretty straightforward? I'm hoping it was. Good, because we're going to start using those equations today. This week is column week, okay? So we're going to be analyzing and designing columns. Today's lecture is going to strongly focus on analysis. Well, I mean, it's all going to be analysis. And we're going to discuss two methods for analysis. Traditionally, in steel design, you would discuss a third method, which is to use what's called Table 4-22 in the manual. I decided to just sort of forego it. I might mention it a little bit later in the semester. Nothing really special about it. It just circumvents a little bit of the math. But between method 1 and method 2, you've got more than enough that you need to assess a column. Okay. Does everybody have the QR code? Everybody get that? Okay. I don't know what happened there. There we go. Say, why wasn't it pulling up? Okay. All right, so let's go back to what we discussed last time. So if you recall, we had sort of ended the lecture when we departed for spring break. We had ended with the sort of assessment of our AISC column curve. And if you recall, the lecture that we had before break, the first thing that we did is we derived this. We derived our elastic buckling stress based on the differential equation solution that Euler contributed in the 1700s. And what we found is that, okay, we've got this solution, and it's fine and all, but it's useful, but it's not enough. And it's not enough because of two reasons. And those two reasons are residual stresses that are baked into the column from the rolling process, and then geometric imperfections, the idea that the column is not perfectly straight or perfectly plumb. And so because it's got a little bit of an imperfection, we have a second order effect that reduces its elastic buckling capacity. So we have these two expressions that we can use to calculate a column's buckling stress, or a nominal buckling stress, based on where the slenderness fits on the curve. And so if we're in the inelastic buckling range, this is our answer, and if we're inelastic, we're here. And the range is dependent upon whether or not your slenderness, what side of the x-axis it falls on when we compare it against this limit here. Which if I use the term anchor point, I'm talking about this right here, this 4.71 square root of E over Fy. And the whole purpose of the homework was so that you could plot that, so you could kind of get familiar with the equations and understand how they work. Okay. I do want to briefly remember or recall the K values for column design. Remember, we're using the recommended values, not the theoretical ones. The theoretical ones are what you would derive using a differential equation solution, but we up those usually a little bit to account for the differences between ideal scenarios and real world scenarios. Okay, so we're going to begin today discussing column analysis. But before I do that, I kind of need to take a second and discuss strong axis behavior versus weak axis behavior. Another term that's also used is major axis behavior versus minor axis behavior. So if I use strong versus weak or major versus minor, it means the same thing. Let's talk about those definitions, okay? Now I'm going to focus my discussion and really our discussion for the rest of the semester, I should say, on W shapes. So all of our column and beam problems for pretty much the rest of the semester are going to be W sections, okay? Because columns and beams in building, they're the most common shapes that you would use, okay? Excuse me. Okay, so if we look at W sections and we open up the steel manual, just for any W section, we have a column of, or a series of columns of values representing the x-axis and then the y-axis. Now, if we look at our radii of gyration, and we've already sort of seen this before, but you'll notice that for pretty much all W shapes, if you just pick one, you'll find that Rx is always bigger. Okay, Rx is always bigger than Ry. So much so that we'll call Rx, I'll typically call Rx the strong axis, and I'll call Ry the radius of gyration about the weak axis. Okay, and again, we're referred to this way because Rx is bigger than Ry, so that's sort of what that means. Now, that's not always the case. So for example, you can find some WTs or some angles where Rx might be smaller than Ry, but for most routine columns, that's going to be the case, like W shapes and whatnot, that's going to be the deal. Okay? Now, I want to talk about like how the strong axis versus the weak axis can affect capacity, okay? And I want to do that by looking at this, okay? So what I have here is I have a column. I'm going to actually go to the notebook here. I have a column here. Let me detach my keyboard for a second. And I have a W shape, and let's say that it's pinned on both ends. So it's pinned at the bottom and it's pinned at the top, okay? We're going to say that the column is 20 feet long. And for simplicity, I've given you some R values. So Rx we'll say is 6.2 inches and Ry is 4.1 inches, okay? Now because it's pinned, we're going to take the K value to be 1, okay? And if you go back to the slides, you'll see that for a pin column, K is in fact 1, okay? So the question is, how is the column going to buckle? And the question, what I'm basically asking is the column going to buckle about the strong axis, or is the column going to buckle about the weak axis? Now, before we do anything in regards to math, I imagine that a lot of you are thinking, well, it's going to buckle about the weak axis because it's the weak axis. And that's a fair observation, and for this column is in fact true, okay? Now, how can we determine that mathematically? Okay, well, let me show you what I'm talking about. Okay, so the first thing I want to do is I want to determine KL over R for the x-axis, okay? And what that means is that I'm going to find KX LX over RX, okay? Now some of you might be a little confused, like, wait a minute, what's this LX? Because the column's 20 feet long. Bear with me, you'll see what I mean, okay? So I told you that the K values were 1, okay? The column is 20 feet long, and the radius of gyration is 4.10 inches. Before I do any math, does anybody have any problems with this? What's this? This is feet. This is, so maybe what we ought to do is multiply this by that so that we derive or compute a slenderness quantity that's unitless. Remember, when we're calculating L over R's, the member length is usually in feet and the radii of gyration are usually in inches. So we need to multiply the member length by 12 so that we have inches over inches, right? So I'm throwing that out there now because that's an easy thing to forget when we're doing column analysis. Okay, so somebody help me out. What is this? It's Monday. We just got back from spring break. You're making us break out the Casio FX115 ES Plus or similar scientific calculator? And my response to that is it's probably been 10 days since you used the Casio FX115 ES Plus or similar scientific calculator. I figured you would miss it, you know? 58.5. Okay, so we'll, 58.5. So I'm already making mistakes because I put the wrong radius. Down here, the other one's going to be 58.5. Here I am, you know. I must have had my break was too long. Sorry, wrong radius. 38.7. So we'll call this 38.7 and then hold that. What's that? Second? Okay. So for the next one, we'll do KY, LY over RY, which is basically the same calculation, but now 4.10. And then that's 12 inches per foot. And what was this one again? 58.5. Okay. All right. So, okay, remind me, what does the column curve look like? It sort of does this whole thing, right? So if I were to sketch that out, if I were to say, okay, here's the column curve, what goes on the x-axis? Bless you. KL over R. And then on the y-axis is Fn, which essentially what that means for the purposes of our discussion is Fn is the column's strength, its capacity, right? And when we plot it, curve looks something about like that. Is that a fair assessment? And essentially what is true about the curve is that as your slenderness value increases, the column's capacity goes down, right? I mean, as columns get slender and slender, more and more slender, they're going to be more apt to buckle, right? They're going to want to buckle more likely. Is everybody with me on that? So my question is, from a capacity standpoint, if I asked you which value do we use for computing the capacity, this one or this one, which one do we use? KL over R for the x-axis or KL over R for the y-axis? X. Which is going to yield a higher capacity, X or Y? X is going to yield a higher capacity if we use it. But what I'm saying is if we're taking the column and loading it and loading it and loading it, which buckling load is going to occur first? This one or this one? The Y. So what I'm getting at is this is the value that governs. Okay? Does that make sense? Okay. So for a capacity calculation, this is the value that governs. Now, in this case, the weak axis governed, right? Because KL over R for the y-axis was bigger than KL over R for the x-axis. Does that make sense? The idea that when we're computing slenderness values for a given column, we would use the largest slenderness value to compute capacity because that would be the worst case scenario. Everybody with me so far? Okay. All right. Now, okay, so far so good? Now, I imagine that a question that's swimming in your head right now is, okay, Dr. Mike, I get the whole KL over R's, but what is this? Like, why are you looking at this column and this column, and it's like the same column? Like, what's going on here? Why, I don't understand this. Fair question, okay? Let me give you a sort of three-dimensionally rendered example of what I'm talking about. So let's say that we had a column in a building, okay? So this column, let's say for the sake of discussion that this column is 35 foot long, okay? So the column's 35 foot long, okay? So let's say, for example, we're talking about these columns right here, the exterior wall columns in the building, okay? Now, what's happening this way is we're having floor beams frame into the column at various heights. So we'll say 10 foot, 15 foot, 10 foot. The numbers themselves don't really matter all that much, but just to give you kind of an idea. So the column's 35 foot long, and we have intermediate floors framing in it at different stories. Okay. The thing is, though, is those columns are not framing in both directions. They're only framing in one direction. Okay. So what I'm saying is that if I were to draw this column, and I were to say, okay, here's the column, let's call it the x-axis. Here's the column, let's call this the y-axis. What I might say is that for the x-axis, the column doesn't have any bracing along the length. And so what I might say is, here's the column, maybe something like this, maybe something like this, and this is 35 feet, okay? But along the y-axis, I've got braces framing in, okay? So in other words, I might have, a boundary condition right here, and I might have something like this, where this is 10 feet, this is 15 feet, and this is 10 feet. So in other words, what I'm showing is a different bracing configuration about the x-axis than I am the y-axis. Does that make sense? Are you okay with that? So what I'm saying is that whenever we have a situation like this, what we would have to do is evaluate each bracing configuration separately. Look at the x-axis, figure out the worst case KL over R. Look at the y-axis, figure the worst case KL over R. Make sense? Let's go back to this example, okay? Okay, so let's say, bless you, let's say, okay, here's my example, okay? And what I'm saying is the x-axis and the y-axis are exactly the same. Column's 20 foot long, K is 1 on both sides. So if the K is the same on the both sides, the length is the same on the both sides, then what's going to govern the capacity is basically just the R values. But now what I'm going to do is I'm going to say, wait a minute, now let's look at this, okay? Now let's take the same situation, let's not mess with the strong axis, but let's throw a brace in the middle. Let's put a brace right in the middle of that column along the weak axis, okay? And let's see what happens from a KL over R perspective, okay? So first off, did anything happen here? No. So this is still going to be 38.7, okay? But what about KL over R for the y-axis? What happens here? Well, let's take a look at it. What changed? Well, did the K value change? No. I mean, this is pin, 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 pin. None of the boundary conditions changed. Granted, the length changed. So this is 1.0. Now, instead of a single column segment that's 20 foot long, we have two column segments that are 10 foot long apiece. So now let's look at 10 feet over 4.1 inches times 12 inches per foot. Okay? What would we get here? Well, we'd get half of what we got the last time, which is probably something like 29.3. So now, which slenderness value governs? This one. Okay? Okay, everybody with me so far? All right, let me ask you just a follow-up question just to make sure that we're all on the same page. Would you agree that adding this brace made the column stronger? Now, why are you saying yes? Well, here's how I would say it. Without that brace, the governing slenderness was 58.5. We throw the brace in, the governing slenderness is now 38.7. So by throwing that brace in, we drop the governing slenderness, which is going to up the capacity. Make sense? Okay. If that's the case, then here's sort of a follow-up to that. Would adding braces here help? No, they wouldn't help, right? Because in the end, I could brace this like crazy. This is still going to govern, right? All we're going to do is drop this term, but this one's still going to govern. So there's a point when adding those braces along that weak axis isn't really going to help, okay? Does that make sense? Okay. All right. Any questions so far? Okay, I'm going to erase this. All right, so... Okay. All right. So with that sort of discussion of slenderness out of the way, let's discuss column analysis, okay? And so I'm going to propose, bless you, I'm going to propose two methods, okay? The first method is basically just going to be, straight calculating the capacity. In other words, calculating the capacity using the equations that are in the manual from section E3. You already are familiar with those equations because that's what we did when we plotted our capacity. So using the equations from E3. The other method is going to be using a particular analysis aid in the manual. And that analysis aid is going to be table 4.1a. Okay? 4.1a is sort of a lookup tool that we can use to look up capacity. I want to say a couple things about these. And I'm calling them method 1 and method 2. I don't know that there's any hard and fast rule that you would call them method 1 and method 2. Really, the method is just using the equations and using table 4.1a. Both of these methods will yield the same answer theoretically. And by theoretically, what I'll say is this is going to be a straight calculation. This is going to be interpolating values. So they're going to yield the same answer plus or minus a few decimals because of interpolation. Remember, our curve is nonlinear, and this method is largely going to be interpolating between values in a table. So there's going to be a little bit of error there, okay? But what I'll say is that if you calculate the capacity using method 1 and then calculate the capacity using method 2, barring some issues with rounding, you should get the exact answer. So the two methods can serve as a check for one another. But the reason I'm showing you table 4.1a is because 4.1a is a critical tool for the purposes of design. So much so that if you open up the reference manual that you get when you get to take the FE exam, you will find a snippet of table 4.1a in the FE reference manual because you pretty much can't design columns without it, okay? But we'll get to that a little later, okay? So I want to go through and demonstrate each method on a representative column. So how do we calculate the capacity using table or using section E3? Well, I mean, there's not really anything here that you don't know how to do because this is all just the same equations that we use to plot the capacity in Excel. So we would determine the worst case KL over R for the column, which I think we now kind of have an idea on how to do. We would then compute FE, which is pi squared E over KL over R squared, and then compute Fn, compare the slenderness to our anchor point and use either equation 1 or equation 2. I'll tell you that most columns are using this one, okay? Most columns are using the upper expression, both in analysis and especially in design. And then 0.9 Fn times the gross area. And so I want to demonstrate this method on this column, this particular column. So what I've done here is I've gotten this column and I've drawn its bracing configuration right here, and we're going to calculate the capacity of this column. We're going to assume for the sake of discussion that the column is a W14 by 90 and it's made out of A992 steel. What I'll tell you is that column W shapes with Fy equals 50 KSI is pretty much going to be what we're going to be doing from here on out. Okay, so columns and beams are W shapes with Fy of 50. Okay, there might be a couple deviations from that, but unless otherwise stated, I think you can pretty much assume that. Okay, so let's go through and calculate the capacity of this column. Okay, so let's see what we can do here. All right. So first off, so here's our column. A couple things that we're going to get off the bat right now is we're going to recognize that if this is A992 steel, this is 50, And we know that for a W14 by 90, we can look up any properties that we're going to need. I propose that we're only going to need 3 properties, at least for this problem. Those 3 properties are going to be the gross area, and what are the other 2? Just curious. We need the gross area, but what other 2 properties are we going to need for this column? Rx and Ry, of course. So let's look those up. What is the gross area for a W14 by 90, and what is Rx and Ry? And then Rx and Ry? Okay, 6.14 and 3.7. Okay. All right. Okay. Now, before I scroll down a little bit, I want to take a look at this column bracing scenario, okay? Because we need to start having some common way of referencing these. So what I'm going to do is I'm going to look at each segment independently. So for example, for the x-axis, I only have one segment, so I'm going to call that segment x. So in other words, the length of that segment we'll say is 35 feet long. But for the y-axis, there's going to be a, we'll call it like y1, y2, y3, okay? Now, we're in the learning stage right now, so we're going to go through and assess every segment, but later on, we're going to see how we didn't really need to do that. In fact, we could probably have skipped a few of these segments and it would have made our life a little easier. But we'll talk about that later. Right now, I just want to go through and be systematic with all of them. Okay? Now, for segments that are pinned, in other words, they have a pin on the top and a pin on the bottom, which is the most common boundary condition, we can take our K value to be 1. And that comes straight from the manual as well. So are there any segments that are pinned on the top and pinned on the bottom? Which ones? No. This is a fixed boundary condition. This is fixed, okay? Now let me ask it again. Any segments that are pinned on the top and pinned on the bottom? Y1 and Y2, right? So this one we can say is a K value of 1. This one we can say is a K value of 1. But what about X and what about Y3? What's the deal with X and Y3? It is fixed on the bottom and pinned on the top. And so we need to look up that K value. So that means we need to break out our manual, right? So we're going to be back in the main, we're in the commentary of the specs. This is like 16.1 dash, I think it's like 650. This is definitely a tabbable page, by the way. So we're going to go here to find our K values. Okay, so somebody help me out. What is the K value going to be for when the column is fixed on the bottom but pinned on the top?
0.7.
Say it again.
0.7.
Is it 0.7? Or is it, what'd you say? 0.8. This is 0.8, okay? So you do have to sort of pay attention to the legend, okay? So what I am saying for this bottom boundary condition is that it is restrained against both translation and rotation. Whereas when I have a pin boundary condition, what I'm saying is it's free to rotate but not translate, okay? So fixed translation rotation, fixed translation free rotation, K is going to be 0.8. I believe that's case B. The B or, okay. All right, everybody with me on that? Any questions? Okay, all right. So if that's the case, now what we're going to do, and if it's okay, I'm going to scroll a little bit, so I want to have some room to do this. I'm going to find worst case KL over R, okay? Now, remind me, how many segments do I have? I have 4, right? I have an x-axis, and then I have 3 along the y. Okay? So here's what I'll do. I'll say case. We'll call it x, y1, y2, y3. Okay? Let's write the k value for each case. So what did we say? This was 0.8. This was 1, 1, and 0.8. Is that right? Okay. Okay. What about the length? Okay. What about the length? First off, what units do we really want the length to be in? Inches, right? So what I'll say is this. So for the x-axis, what is the length like that's reported on the diagram? So we'll say 35 feet equals 420 inches. Okay? And then what was it? 10, 15, 10? So 10, 15, 10, which is 120, 180, and 120. Okay? Now what about the R values? Okay, what about the R values? What's the R value going to be for our first axis? 6.14. Okay, and what about these three? 3.7. There we go. So this one's going to be 6.14 inches. So I'm a table guy, as I imagine many of you are. So for each row, each case, we're going to have a KL over R, KL over R, KL over R, KL over R. Make sense? So let's just do the first couple together. What do we get for this one? The first one. 54.7. I am going to add a couple of different decimal places, and there's a reason why. Mainly because when we see this value show up later on in the problem, I just want everybody to see, oh, that's where he got it. So I find that if you add a couple decimal places, it makes that more recognizable. Okay, what about the next one? Let's just do the next one, and then I'll do the rest. 32.432. 32.432. Okay. I've got, for this one, this, and that. Okay. So if I were doing a problem, if I'm doing this problem, I'm trying to determine what is the capacity of the column, which value do I use? The 54.723. So KL over R is that. Okay, is that okay? Everybody all right with that? Now, I want to rewind the clock a little bit to what I had said earlier. I said that we calculated all 4 cases, but if we had used our noggins a little bit, we probably didn't need to calculate all 4 for this problem. Let's go back to the very beginning. Let's go back to this. Okay. Could we, without doing any math, have looked at each of these and figured out which one was going to govern by looking at the y-axis? Which one was going to have the largest KL over R for the y-axis? Y2, right? Y2 simultaneously, so look at the K values. Which one has the largest K value? Well, Y1 and Y2. And of Y1 and Y2, which one's longer? y2. So was it really necessary to compute y1 and y3? No, it wasn't, okay? We're doing it now just so that like we can kind of understand what we're doing. What I'm saying is rewinding the clock a little bit. Would you have done that? Probably not, okay? Does that make sense? Right. So yeah. So by the way, I have no problem if you make that determination on an exam or on a homework where you say, I just don't need to calculate all these. As long as you get the highest KL over R, that's fine. With me so far? Okay. All right. So if that's the case, now, okay, so let's go back to the spreadsheet. Once you had a KL over R, what did you then calculate? FE, right? So we would say, okay, FE is pi squared E over KL over R squared, okay? Now, pi squared times E, what's E? For steel? 29,000 for structural steel. I want that number sort of burned into the back of your head by the time you graduate. Just like Dr. Waite wants 62.4 pounds per cubic foot or 9810, he's in metric lane. So, okay, I want this number burned into the back of your head. Okay, now, for the denominator, I could repeat the calculation, but instead, like, let's just do 54.723 squared, right? Because, I mean, we've already calculated the slenderness. No need to put 0.8 times 420 divided by 6.14 quantity squared because we already did that, okay? So what do we get here? And we'll say, like, 2 decimal places is probably enough. And part of the purpose of doing this together is because some of these equations are a little wonky, and I just want you to feel comfortable calculating them on your Casio FX115 ES Plus or similar scientific calculator, because I know everybody brought the Casio FX115 ES Plus or similar scientific calculator to class, right? Everybody brought the Casio. Everybody in this row brought the Casio. Everybody in this row brought the Casio. The second row. I love my job. What do we get for this? 95.58. Second? Yeah. Okay. Now, once we calculate FE, what's our next goal? We need to calculate F sub n. And how do we do that? Well, we have to compare KL over R to our anchor point, right? So KL over R is, let me just sort of write that. So KL over R is 54.723. And then our anchor point is what? Is it 4.71 times the square root of E over Fy? I'll just say this, and this will become much more clear throughout the rest of the semester, but this idea of a number times the square root of E over Fy shows up quite a bit when we do stability-related calcs. You'll see this pop up a lot with columns and beams and whatnot, but that's just a side point. Okay, so 4.71 and then 29,000 over 50. Okay, and what do we get here? Okay, so 113.43. Second? Yep. Okay, so what I'm essentially trying to compare is this term and this term. Okay, and what I'm saying is that KL over R in this case is less than that. And so if it's less than, what we're dealing with is inelastic buckling. And what I'll say is that in most practical analysis and design problems, that's where you're going to be, is in inelastic buckling. If you're in the elastic zone, I'm not saying it doesn't happen, and I mean it can happen for, I would say, like light construction where you have really, really low loads, but for maybe like a building like this, like if we're talking about an interior column, probably not. So, okay. So if that's the case, our FN is 0.658 raised to the Fy over Fe. Remember, this fraction is an exponent to this, okay? And so this is then multiplied by Fy. Let me lower this just a tad. I'm sort of cartoonishly drawing that much lower. And then that was 95.58. And then times 50. Again, really trying to hammer home the point that this is an exponent to that. Okay? All right. Now, I will, let's just see what you're getting for an answer. Because I want to make a point about the numerical value that you get as a means of checking yourself during homeworks and exams. $40.16. Do I have a second? Okay, all right, I saw all the seconds. Okay, so just on a side note, okay, let's go back to the column curve. So this is KL over R, this is FN, and the column curve looks something like that, right? So as KL over R increases, FN decreases, right? But can somebody remind me, what is the FN value right there? At KL over R equals 0, FN is equal to, in this case, 50, but more generally, it's equal to Fy, right? Okay? What I'm getting at is this. What if you did a calculation on an exam and for this value you got this? Would that be right? That wouldn't be right. It couldn't be right. Why? Because it can't be bigger than Fy. You see what I mean? So I'm trying to give you just like a gut check when you're doing a homework problem or doing an exam problem. This has to be smaller than Fy, okay? It's got to be. So I'm just throwing that out there as a calculation. So if you're in the 40s or 30s, you're probably doing something right. Okay. So therefore, phi PN is 0.9 FNAG, which is 0.9 40.16. What was AG again? 26.5. And so phi PN is what? We'll say to like 1 decimal place, because at this point you're fine. 957.8 kips. Do I have a second on that? Okay. Okay. So that's how we would compute the capacity according to the spec. Okay. So 957, 958, something about like that, okay? Now, we're doing some rounding, you know, we're rounding this to decimal places, we're rounding that, rounding this. So if you were to do this in Excel, you might get a slightly different answer where it's tracking decimals. But by and large, that's going to be about what it is, okay? Any questions on that? So that should be pretty straightforward. Okay. All right, any questions? All right, if that's the case, I do want to at least introduce the second method. We're not going to have time to fully discuss it, which is fine, because that wasn't really our goal today. I wanted to mainly focus on the axis identification in method 1, but I do want to discuss method 2, okay? Method 2, first off, this table is definitely something that I would have in the manual. It starts on page 4-12, and table 4.1 goes on for quite a few pages. I mean, it's like 20, 30 pages long, so you're going to be flipping through it quite a bit, okay? I think we would all agree that some of the computations that we've done so far, I mean, they're kind of involved. I mean, you know, like when we were doing tension members, this isn't 0.9 FYAG. This was a lot more to it, you know. There was a lot more identification. Even tension members, like this arguably could be thought of as a little bit more involved than just like a net section fracture computation, okay? Table 4.1a makes our life a lot easier for looking up capacity. Now, just so everybody's aware, there's a table 4.1a, but then there's also a 4.1b and a 4.1c. So please make sure that you're in the right table when you're using it, because the difference is they're different yield stresses. 4.1a is for 50 KSI. 4.1b is like 65. 4.1c is like 70. Okay. All right. So here's the rub with table 4.1a, and I'm just going to highlight this, and we'll discuss it a little bit more later. Table 4.1a lists your capacity based on the weak axis, okay? But for example, for the problem that we just did the weak axis govern? No, the strong axis govern, right? Because it was the x-axis that had the largest KL over R. So what you've got to do is you have to do a conversion, okay? So essentially what you do is you set KLX equal, or KL over R for the x-axis equal to KL over R for the y-axis. And what you do is you solve for this, okay? And what you get is you get kx times lx divided by this ratio. And so the idea is that what you could do is if the weak axis governs, just look up the value for the y-axis. But if the strong axis governs, you have to take the strong axis and you sort of have to convert it a little bit to sort of an apples to apples comparison. And so what you do is you divide it by the ratio of Rx over Ry, which by the way is at the bottom for every section in the table. Okay, so the idea is that if your weak axis governs, just look up the capacity. But if this is bigger, or if you don't know whether or not it governs, look up the capacity based off either this or that, and that's computed like this. And don't worry, that's a topic for discussion on Wednesday, is how we're going to use this. Again, make sure that you use table 4.1a for 50 KSI. If you're using different yield strengths, the manual gives you different tables to use. Okay, and I will say, y'all remember this? We are going to be doing this. So the old linear interpolation. So what we're going to do on Wednesday is we're going to do this problem again, but we're going to do it using table 4.1. And the whole goal of Wednesday's lecture is to get familiar with table 4.1, because you need table 4.1 for design. And we'll talk about that on Wednesday. But I'm going to pull the QR code up again. That's all I got, everybody. I will see you all on Wednesday.